Hello, everyone. This is the lecture for sections 2.3, the limit laws. So from section 2.2, we at least now have a good intuitive definition of what a limit is for a function, okay? Now that we have uh, that intuitive definition, we're going to start to define some laws that we can use, something that's always going to be true when we mess with limits, okay? That's the basis for this entire section. And we're going to develop a little bit more, a couple more theorems that become really useful later on in the course, okay? So let's go ahead and start with the limit laws, okay? So for the next couple of sections for chapter 2, you're more than welcome to use any of these, okay? And I'm going to show you guys how to use them as we move along, okay? So suppose we have a function f and we have a function g, okay? Such that the limit as we approach a specific value a for f is L, and the limit as x approaches a of g is m, okay? They exist, they're whole numbers, L, M, and let's take another value C, we're gonna need that in a second, being all real numbers, okay? They are values, they are legit, they are not, does not exist, okay? And the following statements are always going to be true, okay? The limit as x approaches a of a value c is always going to be that value c, okay? Graphically, that's going to be a line across the value c. So as we approach any value, it's always going to be c, okay? This is the big one that we're going to be using on a regular basis, okay? The limit as x approaches a of f of x is always going to be f of a if the value a exists in the domain of f, okay? Basically saying that we can plug in the value if a is in our domain, okay? The next couple are sort of gimmies. You know, use your gut here. They still work out. Suppose you have the limit as x approaches a of f of x plus or minus, it doesn't matter which one you use, plus or minus g of x. So let's say you have the sum or difference of two functions, okay? Then it is equivalent to the sum of both of them separately. And since each one is already defined, that's also going to be L plus M or minus M, okay? So basically you can break up a sum or a difference of a limit into each respective limit and then find each one separately, okay? The next one down, suppose you have a function f of x and you multiply it by c, okay? And you try to find the limit as x approaches a of that function, okay? So that c is multiplied. All you get to do is, if you guys take a look here, the c gets to pop out in front of the limit. Basically, what you're basically saying here is that the limit just, you don't have to care about it until the very end. You can just find the limit of f of x itself, okay? The next one. Suppose you had a product, okay? Suppose you had the limit as x approaches a of f of x times g of x. Then you can break up the product into each respective limit and then multiply the consequential limits at the very end, okay? You guys see how, hopefully you guys are seeing how these sort of make sense. They work as you would want them to, right? 6. Suppose you have the limit as x approaches a of f of x divided by g of x. So you're dividing two functions, okay? Then you can find the limit of the top and then find the limit of the bottom and just divide them at the very end, okay? So long as the limit of the bottom is not equal to 0, okay? That's the only crucial bit, okay? 7, suppose that you want to find the limit of your function f of x that's going to be to a power, okay? What this basically says is the power just gets to go outside. You get to find the limit as x approaches a of f of x by itself, and then you can take the result and just take that to the power n, okay? And then the last one is sort of an extension of number 7. Let's say you have the nth root of a function, okay? That's equivalent to finding the limit of the function and then taking the square root. So that means you can just take the resultant value and take it to the nth power, okay? So let's go ahead and move to the example here, okay? The first one at least, okay? So let's go ahead and take the limit of this function right here, okay? This is going to be overly explained, okay? You don't have to do this, but it sort of touches on each one of the rules that we did just now, okay? So in order to find this limit, this is equivalent. This is the equivalent to finding the square root of the limit as x approaches 2 of 2x cubed plus 9. And now let me put the square root there. Plus the limit as x approaches 2 of 2x minus 1 and all of this squared. Okay, I can break up these two limits even more, but in the interest of time, I'm going to go ahead and stop here and just go ahead and compute each one of these. So notice that both of these in blue, both of these that I highlighted in blue, there's no problem with me just plugging in x equal 2, because 2 is in the domain of both of those functions, right? So if I do so, I'm going to get the following. This is going to be 25, the square root of 25. And this right here is going to be 3 squared. That's what's going to happen for that tail bit, right? And if we go ahead and put these both together, we get the answer 14. And we are done. Okay. So like I said, this is overly explained. Okay. Notice that for this example, okay, 2 is in the domain of the entire thing. I could have easily plugged in x equal 2 to both parts. Okay. So let's take a look at another one. So what I just did for the first example was just sort of plugged it in and used the rules from above to find my values, right? Okay. Obviously, this is not what's going to happen on a regular basis, right? What we're going to do, what's usually going to happen when you find a limit like this, is you're going to look at the limit as x approaches 2, look at the function that you're looking at, and sort of realize that 2, there's no problem with me just plugging in 2. It is in the domain. Make sense? So I can go ahead, this is what is going to happen more often than not when you guys do these limit problems, is you just get to plug it in. So it's going to be 2 squared minus 2 all over 2 cubed minus 3 times 2 plus 5. And this is going to be, 2 over 7. Okay. So this is how to find just good old regular limits. Notice that for both of these, the value 2 is in the domain. So there was no problem with me plugging it in. Okay. So I want you guys to practice some of this in your quick checks. These are probably going to be really quick. Okay. Discuss them with your group mates. Okay. So in the previous examples, like I said, and in the group, in the quick checks that I just showed you above, the x value was in the domain of the function. There was no problem with us plugging it in. Okay. It becomes a little harder when we have functions and x values where the x value that we want to plug in is not in the domain of our function. Okay. So that's what this next example is going to show us. Okay. So let's say we want to evaluate this following limit, verify my answers using graphing utility. Okay. So I have this function, x cubed minus 1 over x squared minus 1. And I want to find the limit of this function as x approaches 1. Okay. The graph is over on the right-hand side. And if we just go ahead and look at this graphically, like we did before in section 2.2, we can see that it's going somewhere. It looks to be going to about 1.5 or 3 halves. Okay. Now, if we go ahead and plug in, so 1 cubed minus 1 over 1 squared minus 1. So it's going to be 1 over 0. Oh, sorry, 0 over 0, right? This is not getting us what the graph is telling us, okay? And this is because bottom, if we plugged in x equal 1, that's going to get us a divide by 0. So then that means we have to do something else here, okay? So the one thing I'm going to have you guys recall from high school is something from for how to factor these terms out, okay? And specifically, the rule that we're going to be using is the difference of cubes. Okay, and the formula for this, okay, is if you have a cubed minus b cubed, that is equal to a minus b, a squared plus ab plus b squared. So this is the rule from high school we're going to use, okay? And what I'm going to do is I'm going to rewrite this function up here, this whole statement, using that difference of cubes, okay? So here we go. I'm going to try to do, whoops. Come on, there we go. The limit as x approaches 1, x cubed minus 1 over x squared minus 1. I'm going to use the difference of cubes on the top. So according to my rule here, this is going to be equivalent to x minus 1, x squared plus x plus 1, all divided by x squared minus 1. And the bottom can also reduce. So I'm going to get x minus 1, x squared plus x plus 1, all divided by the bottom factors too. So I'm going to get x minus 1, x plus 1. So notice all I did was factored. Okay. This is, that's all I needed to do. Okay. Now, what I want everyone to notice now is notice that there's a minus 1 on the bottom and a minus 1 on the top as well. They get to cancel. So what ends up happening now is this. This thing turns into the limit as x approaches 1 of x squared plus x plus 1 all over x plus 1. Okay. Now, so this limit is now equivalent to finding whatever this limit is. But now, the problem that we had before is no longer there. I can go ahead now for this newly updated expression. I can go ahead and plug in 1, no problem. And that's exactly what I'm going to do. So now this is going to be 1 squared plus 1 over 1 plus 1. 3 halves. Just how we had seen it in the graph to the right. Okay, so this is how we find limits algebraically. This is one of the most simplest ones we can do, but I want everyone to notice the game plan here. The problem was that we couldn't plug in x equal 1 to our function. It made us do something mathematically illegal, okay? So our goal in life, our game plan for any one of these problems, if that so happens, is to eliminate that problem somehow, some way. And all mathematical tricks are fair game, okay? That's game plan. That's the problem-solving strategy for finding these limits algebraically. Mathematically eliminate terms that contain values not in the domain of f of x by any means necessary. However you need to do it mathematically, do it, okay? So that leaves the door open for multiple methods for how to solve these kinds of problems, okay? So for the second quick check, there are a couple common ones here, okay? This is gonna require you to go back into your pre-calc notes and find out how to do these. Some of these are just need, like it says right there, common denominators, okay? Go back to your notes and look at how to do them. I'm giving you the hint of how specifically how to do these using this, okay? Let's go ahead and move on. Now that we have a good understanding or a good working method for how to solve limits, let's get into some theorems for limits, okay? A little heavier ones. So the first one is basically preserving the order of a limit, okay? So suppose that you have a function f of x that is always going to be smaller than g of x, okay? Except near x equal a, okay? Suppose that there's an order that f of x is less than or equal to g of x, okay? And both the limits for f and g exist when you approach x equal a. Then the limit should also keep the order, okay? As I said, I like pictures. So let's go ahead and show you the pictures for these. So suppose you had two functions, okay? Here's a top function, right? And here's a bottom function, right? So the top function is our g of x, and our bottom function is f of x, okay? And suppose we want to approach a value x equal a, right? Then those limits must also follow suit. So then if this is L and this is M, right? Then L should always be less than or equal to M. Simple as that, okay? Let's move on. This one is a really important one. This is actually used a fair amount in higher level math. It's called the squeeze theorem, and there's a reason why we call it the squeeze theorem. It's essentially we're squeezing one function in between two other ones above and below. Okay, so let me read out the theorem itself. Suppose that you have an f, an h, and a g in that order, and that's the order that the y values appear in. So f of x is less than or equal to h of x, and it's less than equal to g of x when x is near a, except possibly at a, okay? And suppose, okay, that the limit of the smallest function is equal to the limit of the biggest function, and both of those limits are equal to L, okay? Then we can conclude that the limit as x approaches a of h of x, that middle function, is also equal to L. So essentially we squeezed the value for h of x by using f of x above, f of x below and g of x above. So let's go ahead and draw the picture of it, right? So suppose we had three functions. Let's say we had a g of x up above right here. So this is my g of x, okay? Suppose I had an f of x below it. Okay, I'm gonna make them touch right there. And this is f of x, okay? And we had an h of x that was always in between them, okay? So here's h of x, okay? Whoa, sorry about that. Sometimes my computer glitches here and there. There we go, okay? So obviously what we can see already is, let's say we want to head toward this point right here. This is my point x equal a. Okay. Suppose that's our value right there. Okay. So notice that as I approach on G, from the positive and negative, both of those are heading toward my value L, right? And then same thing for F, that if I approach F from the positive and negative, that's also approaching L, okay? Then my H of X must follow suit. Essentially, like I said, we're squeezing the function F of X. We're squeezing the function H of X at X approaches A by using G of X from above, F of X from below, and they're approaching the exact same point. Hence the reason why we call it a squeeze theorem. So why is this important? Why do we need this? This is one of the most overly simplified examples, but it sort of drives the point home pretty darn good, okay? We're gonna go ahead and use the squeeze theorem to show that this function, x squared times cosine of x, is equal to 0. Now, the function x squared cosine of x is this right here. It's this red line here, okay? We need to show that limit as we approach 0 is actually indeed 0. We can see it graphically, right? But we want to have a little bit more of a robust way of figuring this out, at least so we can use the squeeze theorem on it, right? So to display how the squeeze theorem is used. The two functions that are above and below, the function above, this is x squared, and the function below is minus x squared, okay? So I want everybody to look at this really quick, okay? We're gonna notice this, that the order is like this for the squeeze theorem. Minus x squared less than or equal to x squared cosine of x, x squared. So what that is saying is that this function right here, the x squared function, is always bigger than our function. And this function right here is always smaller than our function, okay? Next step, we can see from here that the limit as x approaches 0 of minus x squared, that is going to be 0. And the limit as x approaches 0 of x squared, the positive function, that is also going to be 0. Okay, so because of these two things, this right here, and both of these two things right here, okay, we are squeezing our function highlighted in yellow, x squared cosine x, we're squeezing it from above and from below using these two functions. They have the same limit. So then both of these statements in orange together can tell us by the squeeze theorem, right? That the limit as x approaches 0 of x squared cosine of x must also be 0. Okay, like I said, this is overly simplified. This theorem is used much more in higher level math. You just got to believe me on that one, okay? And I believe that is it. Lecture questions comes after this. If there are any questions, please let me know. Come visit me in my Zoom room, and I'll see everybody around.